Please take your seat. Please take your seat. And so now it is my great pleasure and honor to introduce our keynote speaker, and that is Stephen Chu, who is the William Keenan Professor of Physics and Professor of Molecular and Cellular Physiology at Stanford University, a Nobel laureate, former Secretary of Energy, a great friend to many of us, and a visionary whose vision I think you'll appreciate very much. Steve.
Thank you, Rod. It's certainly a pleasure to be here, and I know you're tired and it's been a long day, so I'm going to make you suffer through one more talk. And it's going to be in celebration of light. So very quickly, to remind you, it's already been mentioned that light creates photosynthesis, but photosynthesis in cyanobacteria create oxygen. And here you see a timeline. The Earth is about 4.5 billion years old. We don't really know when life emerged, but looking backward from the right-hand side, that's 3 is 3 billion years ago, 2 is 2 billion years ago, life started. Photosynthetic life started, which started to make oxygen, but it didn't do much. It just crept along because there was a lot of iron and other stuff and absorbed it. So it goes along, it finally saturates, and all of a sudden there's a big, huge explosion of life in that peak. But after that peak, that was not nuclear holocaust. That was the biggest extinction, but during this peak, plants just flowered. And it was those plants during that peak that is responsible for most of our fossil fuel. And so you just have to think fossil fuel is buried sunlight. It really is. It happened a long time ago, 200 or 300 million years ago, for about 100 million years. And in the next 20 or 50 or 300 years, we'll use it all up, but never mind. There are more serious problems. So it's buried sunlight. There's another thing I want to point out. If you look back, and it gets pretty sketchy, in all honesty, back to the paleoclimate history, going back hundreds of millions of years, it gets really dicey about measuring the temperature, measuring all sorts of things. However, there appears to be two stable modes of the Earth. One which is kind of now, with a couple of glaciation periods, and there's another period of the Earth which was warmer. How much warmer? It was about 10 degrees warmer. Most of the time, the Earth spent 10 degrees warmer. So this is one of the things you should think about. There is no exquisite thermostat that says, oh, we can do whatever we want, like our bodies will maintain us at 98.6. Not a problem. It actually the Earth spends most of its time at a very hot temperature. And that hotter temperature, 10 degrees hotter, is very different. Dragonflies had wingspans in the Carboniferous era of 2 feet. Okay, so don't get bitten by a dragonfly. And you notice, so that red bottom dashed line is where we are today. A little bit higher, all of Antarctica melts, but Antarctica melts, all of Greenland's melted, and the seas are 90 meters higher. So one of the things that I do worry about is we seem to have a bistable Earth, and it prefers warmer. So if you nudge it towards warmer, you might be doing something. All right, now, there's one golden rule about public lectures. Well, there's several golden rules. It's their ABCs. It's always be careful, and their XYZ is examine your zipper. However, never use equations. People are scared of equations. They have panic attacks. So here's some equations. So you can get over it. These are Maxwell's equations. I'm not going to explain to you what they mean. If you know what they mean, you say, you're comforted, like F equals ma or E equals mc squared. If you don't know what it means, it doesn't matter. Well, what does matter, and I want to point this out to the engineers and physicists, is this epsilon 0 and this mu 0 are static electric and magnetic properties of matter. And yet when Maxwell wrote the equations down, he found that static properties predicted a wave equation that predicted the speed of light. Amazing. In fact, he goes and muddles through and finds some equations, and he says, this velocity is so nearly that of light, it seems we have strong reason to conclude that light itself is an electromagnetic disturbance in the form of waves according to electromagnetic laws. What are the laws you're talking about? It's Ampere's law, it's Faraday's law, it's stuff like that. Okay? So now you think this great revelation, a dawning of a new light. The first person who actually showed that electromagnetic disturbances actually propagate pretty close to the speed of light was a guy named Heinrich Hertz. And he does the experiment in 1887, and he says, this is of no use whatsoever. It's just an experiment that proves Meister Maxwell was right. We have these mysterious electromagnetic waves. We cannot see them with the naked eye, but they're there. That was it. Okay, now, he didn't fully appreciate what was going to happen 1 or 2 years later, that the world went berserk because they knew they can communicate with radio waves. It was only a couple of years later. But there were other people who did begin to appreciate a little bit later. And Albert Einstein said, this change in the conception of reality is the most profound and most fruitful that physics has ever experienced since the time of Newton. Why did he say that? He goes on in a later paper to say, Maxwell showed that the equations alone appeared as the essential thing, and the strength of the fields as the ultimate identities, not to be reduced to anything else. Everything before that was based on mechanical models. In fact, every wave before that had a medium in which it had to go. Sound waves, waves on a string, waves on a guitar string, you name it. Always had a medium. And all of a sudden, there was no medium. Maxwell constructed a medium. And he had difficulty with it. It was artificial. He knew it was artificial. He struggled with it for several years. And finally, he said, look, this is a little bit slipshod and ad hoc. And so he said, finally, like the Cheshire Cat, the only thing that really mattered were the equations, not the construct of this mechanical model. And that's what Einstein was talking about. It's those equations and those field equations that had a life of their own, and there's nothing mechanical about it. To this day, we don't know what's waving. Just so you know, we're not any wiser than it was in 1865. All right, so let me move on and talk about another thing. Suppose you have an atom, and for whatever bizarre reason, you want to cool it down. So you know that light is scattered by an atom. So if you know which direction it's going, you just point a laser at it and you slow it down. Now, the trouble with this is the atom may be going towards the right, or it may be going towards the left. And so if you really want to cool down a gas of atoms, you have to figure out which way it's going. But you don't know which way it goes, but some are going this way and some are going that way. So here's the trick. It's using the Doppler effect. Now, for those of you who don't know the Doppler effect, let me demonstrate this to you. As I walk toward you, my voice is very high, and as I walk away from you, my voice is very low. Okay? So the atom is going towards that laser beam, and it's tuning that beam into resonance, so it scatters more photons, and it gets pushed that way. You can point another beam in the opposite direction. If the atom happens to be going in the opposite direction, it scatters more light from this beam than that beam. So no matter which way it goes, it wants to be slowed up. All right, that's great. In this one dimension, this atom is going to be slowed down. If the atom happens to be going in this direction, well, you just put 2 more laser beams, and then you can put 2 more in and out of the screen. And so you add up all the velocities. This was a great idea, I have to say. This was a really great idea. These guys stole it from me 10 years before I thought of it. Art Schall and Ted Hensch wrote a paper in 1975 in a 2-page paper describing this, not exactly in this way, but it's surround the atom with light and it will be slow. So I did this experiment. I didn't invent the method. I only invented the name. If you surround atoms with light going in all 6 directions, it acts as a goo, a molasses. And so that turned out to work very well. And in 1985, in Bell Laboratories, I and my colleagues were able to show that you can get a little bowl of sodium atoms and they get very cold. Now, I was very enthusiastic about this. A year later, we were able to trap atoms. And I went up to my former director, now executive director of Bell Laboratories, and said, it was Bill Brinkman. I said, Bill, you can't believe this. We were able to cool atoms and now they're trapped. Isn't it? And he looked at me, and he's a good manager, so he knew I was excited. And so he said, that's very good, Steve. What are you going to use it for? I said, Bill, I have no idea, but it's really neat. And he looked, same screwball kid. So anyway, what can you do with it? The only thing I knew at the time is if they're really cold, you can throw them up, and they're so cold they turn around due to gravity, and they come down. But during the time they're going up and turning down, you can make very exquisite measurements that turn out to be better clock experiments. That technology, which happened in the early 1989, and then followed up, and it soon became the time standard, but a lot of water has passed under the bridge. Many other researchers are making optical clocks that are going to be, in an absolute value, about 18 decimal places. What does that mean? If you start one of these clocks when the universe was born, you will know what time it is, absolutely, to less than 1 second. Now, you're probably thinking to yourself, who cares? Okay. So I'll tell you why you care, at least not at that level, but the most accurate science experiments are frequency measurements, and they're all tied to time. The most accurately known fundamental constants are actually now defined in terms of time. Length is defined, how far does light travel in a certain bit of time. The volt is defined actually in terms of a frequency. The ohm is defined in terms of frequency. So this is the rule in the ground, the clock. Now, let me explain something kind of cool. We use atomic clocks in what are called global positioning satellites. There are a bunch of satellites, about 24 of them, that circle the globe, and they triangulate, more than triangulate, on where you are, and they can tell where you are, at least as well as the NSA. And, sorry, that's a low blow. And so the United States put 2 satellites up in polar orbit. So as the Earth goes around, these 2 satellites go around in an orbit. Why are they doing this? Because it was found out in the 1960s that if you wanted to lob a 200 megaton warhead halfway around the world, little changes in gravity might make you miss by half a football field. All right? And you really wanted to hit it to 10 yards. And someone turned it around many years later and said, you know, you can make this the reverse problem. If you get a satellite and it perturbs the orbit, you can find out gravitational anomalies. Okay? So in this case, some good came out of something bad. And so there are these 2 satellites. Their height is determined by GPS. The distance between these 2 satellites are monitored with microwave transmitters between them. They can determine the change in distance as they circle over the Earth to less than the width of a human hair with each other. And this is what they can measure. This is Greenland. And they can measure the change in the local gravity over Greenland. Why should the gravity change over Greenland? Well, if there are glaciers melting, there's less density there, and so there's less acceleration due to gravity. So where you see red, you see an increase in the acceleration due to gravity. There's no red. Where you see blue and purple, there's a decrease in the acceleration due to gravity. And in this point here, Jakobshavn Glacier, I'll expand it for you. You see that the resolution is so good, you see summer, winter, summer, winter. You see this is 10 centimeters thick change in ice So it has a few centimeters over 2 kilometers worth of ice in the center, and it's shrinking, and it's accelerating. And since it's in polar orbit and the Earth goes around it, you can measure gravity everywhere around the world. And what they're finding is there's a few places where mass is increasing, but most of the places it's decreasing. The glaciers are melting. But this is a much more trustworthy test than measuring pictures of glaciers melting. Okay? So now here's something really cool. This noise floor here is, and if going from x-axis over here to over here is you're having better spatial determination. You can tell laterally changes in gravity. And so the data I just showed you shows this change in gravity, but it's averaging over a big hunk of Greenland. It turns out if you use laser-cooled atoms and split the atoms apart and use the wave-like nature of the atoms and bring them back together again, it could make a better gradiometer for gravity. And so this satellite mission is being designed now by the student who did this work in my lab in 1990-91, and he's now a professor at Stanford, and they think they can be 100 times better. Now a single satellite using light to drop atoms in an interferometer. Now, I can honestly tell you I had no idea that what we were doing would lead to better monitoring of climate change. It's an amazing thing about science this way. So, all right, some other new surprises that came out. Remember I told the executive director of Bell Labs I had no idea what it was good for, but as soon as it happened, all sorts of ideas came not only to me, but to many, many other people. And one of them was inspired by Art Ashkin, who at the time in the 1970s was dreaming of cooling atoms, but he also was able to trap particles. And while I was at Bell Laboratories in Homedale in 1986 and 87, he found that this same optical trap that was used to hold on to atoms was really good at holding on to bacteria, wiggly little animals. He found, now the way he tells it's not exactly probably true, but he found that if you take New Jersey water and you just leave it on the microscope slide for a few days, something grows. But anyway, so he was able to trap and move around bacteria, and if you turn up the intensity, he could opticute them, and that's terrible. You couldn't do that in university. But when I got to Stanford, I said, is it possible to hold on to an individual molecule, and that's not a bacterium, with light? And so this is what we did. That little line of light is a single molecule of DNA. The focused laser beam is directed into an optical microscope, and its position was controlled by a joystick. And to my graduate students, it was like playing video games. And so they would disappear for hours just doing this. And finally, after 3 days, they said, you're having a lot of fun, but we should do some science. And that opened up a lot of things. Switching gears. I'm going back to climate change. Depending on how you counted it, I took either a 10-year or a 4 1/3 year sabbatical on energy. And it's been mentioned that solar energy has a lot of promise and a lot of development here at Santa Barbara and other places. This is a map of the solar resources of the United States. It's really very good over here, and it's not bad everywhere else except maybe Seattle and Alaska. Just for comparison, that's Germany. Anyway, but they are the leaders in the installation of solar, and it was actually them. I applaud them because they actually created a market for solar that drove the technology. But we have much better resources. Let me put it on, let me just explain how technology develops. It's called a learning curve. And when you increase, let's say you double the production of something, whether it's a refrigerator or corn or cars or solar modules, or even integrated circuits, the price comes down. And so you double it, it goes down by a certain fraction. You double again, it goes down by a certain fraction. So if you plot this on a logarithmic curve here and a logarithmic curve here, it should follow a straight line. Well, nothing should follow a straight line except it happens to. It's just a fact of life that we don't understand. Many things in technology development follow this learning curve. Many, many little things constantly improving. And so this was made by a company 1366, and it was made in 2008. And they said, well, here's where we are today, and you just follow the slope, and by 2015, we'll be there. But by the end of 2014, we weren't there, we were here, because the deployment actually was increasing rapidly, and even through the Depression. What is this line? This is the price of wholesale electricity in the United States. This is getting very exciting. So now, how did it affect solar deployment in the United States? This is a history from 1985 to 2013. Nothing much happened, and then it started stagnant for a long time. This is the deployed number of solar panels, and then something happened around here. What happened? Well, I became Secretary of Energy. Now, you should be skeptical. You know, correlation does not mean causation. But let me tell you, in this case, it did, because despite all the criticisms of the loan program, most of the loans were not going to innovative solar companies that make new modules. They were going to put them in the field to deploy wind and solar. And in 2009 to 2013, Wall Street didn't want to touch it. It said it's risky. We don't know if you can make money. And after Solyndra and after a few failures, it turns out that we think we're on target to net the government, including the failures, $5 billion of profit. How could you make $5 billion when you're loaning out money at 1.5%, which is required? Okay, so it was not that we were doing better than venture capitalists. We were doing better, way better than Wall Street. What was happening is we wouldn't make a loan to a big firm that wanted to source solar or wind unless they had an agreement of a utility company. We will buy at a certain rate. So what's the risk? If you install it on time, on budget, you make money. And so over those 3 or 4 years, it turned out that they were installed on time, on budget, and it looks like in fact, they were so good about making money, Warren Buffett bought 2 of our solar farms. Or he said, hey, it's bankable. And so we don't actually need the loan program anymore, but we did in 2009 to 13. So that was actually one of the few government interventions that I was given it. I didn't invent it, I have to confess, but it did seem to work. Let me explain to you how well it worked. It's not technical. I'm going to talk about what are called power purchase agreements. You spend $10 million or $100 million or even $500 million, you got to get investor money. You're borrowing at 8%, 10%, 12%. You sign an agreement with a utility company. They will take it, and in July 2008, the contracts were selling for 18, 20 cents a kilowatt hour. By 2014, they were selling for 5 cents a kilowatt hour in the sunny places. That's pretty good. What is 5 cents a kilowatt hour? Well, if you build a new natural gas plant and you assume that natural gas stays at $4 a million BTU, which is anomalously low for the next 50 years, the life of the plant, it's the same price. The remarkable thing is solar and wind get cheaper and cheaper and becoming competitive without subsidy with fossil. The fossil guys are getting very agitated, and they're trying to convince everybody that it will always be more expensive. But it's not going to be. Within a decade, without any subsidy, it will be, at least let me be careful, at the 10 and 20% solution, it will be cheaper. When you're 50% renewables, then the cost of the backup and the transmission counts as part of the cost. But in 20 or 30 years when we're there, it will be competitive. So this is very good news. All right, this is where the solar is around the world. And you assume a 15% conversion efficiency, and you ask how much land it will take. Well, you can't build solar in cities, but if you average it over here, those little white squares are enough to satisfy today's electrical needs. You probably can't see the little white squares, so I'll make them bigger. That's 10 times today's electrical needs. So it's not a matter of land if you can transmit the energy from less populated areas to more populated areas, and then rooftops also. But there is an opportunity here. There's another opportunity. If you truck diesel fuel in to create electricity, solar is 2 to 3 times cheaper today without subsidy. It's just plain cheaper. And then you ask, well, and they can be pretty robust. And so what is it that people, let's say in developing countries, want more than anything else once they have electricity? Turns out it's a cell phone. A number 1, cell phone. A number 2, clean lighting instead of kerosene lamps. They want refrigeration, a village refrigerator, but most people don't want those big 20-foot refrigerators that Americans use. There's no Costco in sub-Saharan Africa, and they don't have freezers. So you can imagine a smaller, compact, well-insulated refrigerator, but instead of the freezer, there's a hunk of water, and you cool it down, and then when solar's up. So you can probably keep this thing going, and you still need diesel for backup. Water purification, sunshine, you purify water. That's water storage, energy storage, right? When the wind blew in the Midwest 150 years ago, we pumped water. That's a pretty good battery. Now we're used to flicking on a switch. And so we have to rethink how much battery we really need. I'm going to switch gears again. I'm going to talk about Leeuwenhoek and the microscope. He made the first really good microscope. Believe it or not, that's what it is. It's a single lens. And the compound microscope was that lens in your eye. And rumors started floating around that this guy came out of nowhere and is making a really good microscope. And it got back to the Royal Society. And they invited him to write a paper on it. And so he submitted a paper, and this is what they said. Your letter of October 10th has been received here with amusement. Your account of the myriad little animals seen swimming in rainwater led one member to imagine that your rainwater might have contained an ample portion of distilled spirits imbibed by the investigator. This is actually in the letter. It has been decided not to publish your communication. However, all here wish your little animals health, prodigality, and good husbandry by their ingenious discoverer. Now that's a rejection. But word got out that they were real, and then Robert Hooke, who was also investigating the microscope, was in panic because he found Leeuwenhoek's microscope was so much better than anything anyone else could make, and Leeuwenhoek wasn't telling anybody how to make it. And he was afraid when Leeuwenhoek dies, the whole field would be set back. Now, I'm going to go back and show you a little bit about this. That's a little glass bead. He drew a fiber. He flame polished it. It turns out when the little glass bead is really small, lots of diffraction helps you, and it's really smooth, and it goes into a little bubble. That was it. How cool is that? Anyway, he wasn't the first microscope. This is a bigger version of a microscope. Nobody invents anything. They're always following on. Let me tell you about what's happening in optical microscopy. The 2014 Nobel Prize was shared in chemistry, was shared by 3 physicists, W.E. Murner, Eric Betzig, and Stefan Hell, for inventing a way of overcoming the so-called diffraction limit. What's the diffraction limit? If you have a point emitter of light, diffraction, based on the wavelength of the light and how much you collect of the light, is a blur circle. And it can get as good as 200, 250 nanometers. And so if you had a bunch of these all together, you couldn't distinguish that you had 4 little dots. But if you saw them one at a time and found the center of each dot one at a time, you could find out where that one is, that one is, that one is, and they don't blur together. So this was one of the essential ideas. This is what you see in an optical microscope, a standard optical microscope. This is what you see in the so-called super-resolution microscope. It looks a little better, but let's expand that. That's what it looks like, and you can expand that even more. And you can localize the position of molecules in a cell to 10, 20 nanometers, getting to be molecular scale. It's just better. This was done in a dead fixed cell by Eric Betzig. This was essentially the paper that got him his part of the Nobel Prize. Again, a conventional microscope, we said this was really cool. And so this is an E. coli bacteria, about a micron in size. And what we're doing, now this is alive, it's not dead, and these little bubbles are proteins being excreted by the microbe to make a fortress to protect itself against onslaught. So it's making a cellular fortress. And so these, and you can blow that up and you see this, okay? But there's a problem with this stuff. This, it's better than that. The problem is it takes a while to get these images, up to roughly a minute. That the best stuff is done either in dead cells or in cells that have very rigid matrices that are not moving. If you try to label a live protein, even on the surface of a membrane or in the middle of a cell, Brownian motion smears it out. So in the time it takes to collect the photons, you're back to normal resolution. So it doesn't really work except in dead cells or in rigid cellular matrices. And so when I got out of the Department of Energy, I said, well, there's all sorts of things I wanted to do and many other people wanted to do if you had better probes. And so it was kind of a Christmas wish list. What if you had what? What if you want 10 nanometer spatial resolution, you want to label multiple proteins, and you want to follow the dynamics on live stuff, so they have to be pretty bright. So I'm going to talk about 2 things we're exploring, and it's a progress report. I got a lab, let's see, it was in July or August of 2014. And, you come out of the Department of Energy, and I go back to Stanford, and I still have to wait a year and a half for a lab. My old lab space they gave to another professor who will get a Nobel Prize, Karl Desseroff, and he didn't want to give me his space back. I just don't understand it. But anyway, so we are putting ions in crystals. They are rare earth ions like neodymium. For those of you who know lasers, this is a workhorse laser. This is the energy level structure. You can excite it with a cheap diode laser. It relaxes to this level over here and emits these colors. They are biocompatible. They're absolutely photostable. When your neodymium laser dies, it's because your exciting source is dead. It just, it'll last forever. There are some issues. These things over here are beginning to absorb in the infrared, so you have to synthesize particles with an undoped shell. But that's a technicality. Let me give you one glimpse of why we want to do this. So this is some work that was published when I was Secretary of Energy because I had nothing better to do. No, it's actually because I had a group and I couldn't abandon my group, and I actually found solace Sunday and Saturday night thinking about science. It seemed to me more rational. In any case, we were trying to label proteins having to do with neurotransmission. And so one of my postdocs, Alexandros, was teaming up with me and Tom Sudoff and Axel Brunner, who were professors at Stanford. And we were trying to measure the co-localization of proteins involved with when a neuron fires, there's a voltage spike and it goes and it releases some neurotransmitters. There's a whole bunch of molecules that are involved in this release. Tom Sudoff got a Nobel Prize, I think it was 2014, for his work on this. And it was funny because in September of 2014, I had this idea. So I've been working with Axel Brunger for 12 years. And I said, Axel, let's go get Tom. He's going to be excited about this. So we went, got him, and then half in jest, I said, look, you know, if this works, we could get famous. And then 2 weeks later, he gets the Nobel Prize. So it's too late. But actually, he's a very serious scientist. So he's trying, I'm going to skip this. This has to do with cancer. But let me explain to you why we want to label multiple proteins, not just onesies and twosies, but maybe 3, 4, 5 at a time. Because one of the secrets in biology is you don't really know how they're interacting. They've got to be localized molecularly in order to find out what they're doing. And so we were doing this very painful process 2 at a time, and it was just painful. So if you can localize 4, 5, 6 at a time, it would be great. So we're talking about rare earths now, and this is a postdoc in my group. And it turns out you can put these crystals, you can put neodymium, and it emits that line. You can put ytterbium, and it emits that color, or you can put thulium, and it emits that color. You can get a whole bunch of colors. Now here's the trick. Suppose you have one crystal, and you double it with thulium, and it emits in this color. It's good. You can have another crystal, and you can double it with 2 of the ions. It's not that you have one ion. You have thousands of ions in a single crystal, tens of nanometers big. All right? So it can be half and half. Or it could be just this one. Or it could be a little bit of that and less of that. Or it could be more of that and a little bit of that. You get the idea. If you've got 4 colors, you got 4 factorial combinations. Each class of crystals you target to label a particular protein. So all of a sudden you have combinatorial control over what you do. You can't do this with dyes. You can't do this with quantum dots. So then how do you see this? So there's combinatorial number of probes. It's about 40. If they're sparse, meaning you're labeling cells, not within a cell a cluster of proteins, there's no problem. You can image one of them, and you can locate where they are. You can put it through a dispersive element. And depending on its color combination, you can identify the color, because we now have a spectral fingerprint of that crystal has that spectral fingerprint labeling that protein. Okay? But that's not as interesting, because what you're really interested in is in identifying 3, 4, 5 proteins within 50 nanometers of each other. So how do you do that? Well, there's a cool thing about these probes. They're narrowband absorption. So in one camera exposure, you excite one type of crystal, and you get a color combination. You read it out. And then later, you use a different color light, and you excite a different color, and you read it out. And you go on, and you just read it out. And so you get all sorts of different colors, okay? Because it has narrow excitation as well as narrow emission. So that's something we think might be useful. It was mentioned today, Anya, I don't remember her last name, I only remember her last name when she was an undergraduate with me, Belinsky, I don't know if Anya's here. Oh, there you are. And she was talking about, it was cool stuff, Anya. We are also looking at nano diamonds, and for a couple of things, but these are nano diamonds synthesized from what are called diamondoids. Diamondoids are little molecules of carbon in the form of crystal form of a diamond. And it turns out if you take these and you put them on a substrate and you grow them in CVD, you can grow nanodiamonds. You can grow nitrogen ones, you can grow silicon ones. We're spending some time in the silicon ones because they may be brighter, but they may have other issues. And so, but we'll see. but here's some nano diamonds. They're about 100 nanometers in diameter, and you get lots of counts. You get millions of counts a second from a single silicon vacancy, photostable. But here's the problem. As I actually talked about this, if you want to do NMR really high resolution, that color center has got to be really close to the surface. And so we can make big nano diamonds, and it even looks like a diamond. So, can you imagine proposing to someone with a nano diamond? It's really nearly perfect, so they should appreciate it. This is one that's 8 nanometers or 7 nanometers in size. It has a diamond lattice space and the diamond shape. But the problem is we don't know how close to the surface these particles are, these color centers, as Anya mentioned. Let me just tell you, there's a density functional theory calculation. Walter Krohn here at Santa Barbara got a Nobel Prize in chemistry, 1998, for doing this, that you can actually calculate the energy of a defect, whether it's a nitrogen defect or a silicon defect. And you find that if you anneal this thing to make it a nice crystal, the defect, if it's close to the surface, doesn't want to be in the diamond. It wants to be outside the diamond. And so this is the crux of the problem. How do you get the defect really close to the surface? Nitrogen is better than silicon because it's interstitial, but it's still going to be a problem. And so for those of you who were paying attention to her talk, she mentioned that. But it's kind of cool that some theoretical calculation is actually useful for deciding whether there's parameter space that will allow you to make these, and there is. All right. The good thing about these rare earths and these diamond color centers is they're emitting light in this wavelength range over here where tissue is the most transparent. And this is not our work, but some other person who's injected some particles into a mouse, a bold mouse, and you can actually see through the skin. And so one of the things that we're interested in is if you can get these particles to specifically label a particular cell, whether it's a stem cell or a cancer cell or something like that, because these particles are stable, you can go and you can look where it is, and you come back later and you look where it is and you see if it's moved. And so can you track single cancer cells and maybe cell divisions? Now, so you're thinking, well, how do you see through the skin and without opening up the patient? What do you do? And so there's a trick that was invented in astronomy called adaptive optics. And in astronomy, what makes the stars twinkle is the fact that the index refraction of the low-lying levels of air are changing, and it's just bending the rays. And so a distant star out here, by the time it gets to the telescope, looks like it's jiggling around by a lot. And so what astronomers have been doing over the last couple of decades is they look at a guide star or they make an artificial star. This is a very bright double neodymium YAG laser. And there's up in the distance here, you can make a little light from the sodium fluorescence. And they can take the mirror and they can fix it to take out the twinkle. This has been picked up in microscopy. If you have an optical microscope and you're looking at a sample, you have a perfect wave coming in, coming out, you get diffraction limit. But what if you're going into some thick sample of goo, and this goo is now lensing the light? So it messes it all up. If you can make a deformable mirror that can keep track of this, can you fix it? And the answer is, to varying degrees, yes. It's a very different problem than here, which here it's fast fluctuations but very small index refraction change. Here it's very slow fluctuations but huge index refraction changes. So let me show you a movie. This is taken at Genelia Farms, Howard Hughes medical investigators. This is Naji and Claris. This is using adaptive optics, and I'm going to explain a little bit about this movie. They're looking at a live brain of a mouse, And there's a dye that was invented, a series of dyes that were invented at Howard Hughes Genelia Farms, that if a neuron fires, it allows calcium to come into the neuron. And this dye lights up when calcium rushes into the neuron. And so the neuron actually goes a little bit brighter. And what you're about to see is looking 500 microns into the brain of a mouse. This is no adaptive optics. This is adaptive optics. And what you're seeing in these flashes and these propagating things are neurons firing in real time. Okay? And this is racing ahead with really quick speed. So you can see, and you can get double colors of these things, and you can see neurons of one class interacting with another class, but you see it's subcellular resolution, looking a half a millimeter in. Now, the cool thing about going into the far infrared is those things you can only get through, that's the maximum, about 500 microns. But it looks, if you look at wavelength from 600 to 800, 1 micron, 1.2 microns, this is water absorption and it goes through the roof, so that's not good. And this is, what is this other stuff? Well, you have changes in index of refraction in the cells due to the nuclei, due to the mitochondria. Just think of them as little lenses. And so they're like Coke bottles, droplets on windshield, but now you're looking through dozens of windshields. And the question is, when you're doing that, where do you want to be? You want to be around here, somewhere between 1 micron and 1.2, 1.3 microns. Water absorption isn't kicked in, but the me scatter and everything is minimized. And so the nice thing is those rare earths are actually in here. So this may be another application. This is the work of Hanji Dai at Stanford in chemistry. They shaved the head of a mouse, and they inject some dyes in here, and they're looking in this 1.3 micron range, and you see a better signal than if you're looking at 900 nanometers. It's all fuzzed out because the light's jiggling around. Now, I'm not sure if I haven't, okay. The good thing about this is, so you have the right wavelength, you have a permanent probe, and this was a big signal. They were injecting stuff into the veins of a mouse brain. And so if you want to identify different proteins, you're in a totally different range of ambition. All right. So here's the cool thing. Why is that blacked out? I'm sorry you can't see it. There's another cool thing about these probes. When you shine in light, cells just autofluoresce. There's background fluorescence. They scatter light due to this lensing effect. But the light coming out of the rare earth probes comes out in 100 to a couple hundred microseconds. So if you don't look when you're exciting the probes, and you look 1 microsecond after, you throw away the background. And it works. And I don't know why that's all fuzzed out, so I apologize. But here's a microscope objective. You put this into a secondary objective, and you put a rotating wheel running at 100 hertz. It's got to be a little different than the normal wheel that's a millimeter thick of aluminum. It's got a glass wheel, and you put in chrome patterns. And the reflective chrome, while you're exciting it, blocks the camera, and then it opens it up, and you can integrate for whatever time you program onto your pattern. And then it blocks again, and you open it up, and after tens of microseconds or 100 microseconds, you read it out. So the backgrounds go away, and preliminary experiments say, yes, it does work. And so my former technician, who's the owner and founder, sole owner and founder of Thor Labs, is making us one of these wheels. Here's another application. The probes are good for identifying particular proteins, and maybe we can identify 6 or 10 proteins. But you also want to find out in the context of where these specific proteins are, what's the real scale of biological tissue. Now, the really good thing about electron microscope is its real resolution. It can be a nanometer or better. But it's black and white. You can't see specific proteins. So there have been people looking into taking a sample and putting it in an optical microscope, looking at where the proteins are, transferring the sample to an electron microscope and seeing where they are. The only trouble is if you get greedy and want 5 or 10 nanometer resolution, in the transfer from the optical to the electron microscope, things change by tens of nanometers as a minimum. And so Peter Marr and Max Priggen, two of my postdocs, came up with this wonderful idea. What if we use an electron microscope to image, as you would, but you also collect the light? So this is what is called cathode luminescence. It turns out that rare earths, if you excite them with electrons, give out light. In fact, Rutherford used rare earths to see where alpha particles are hitting the detector. Okay, so that's all it is. It's just combining rare earths in an electron microscope. These are some rare earths we synthesized in my lab. Different colors means that you can detect holmium or erbium, or thulium, and all these other things, just like whatever that song goes, Tom Lehrer. And so you can detect which color is associated with what protein. And so we tried this out. This is the scanning electron microscope image. These are big particles and little particles, and the smallest one is about 20 nanometers. So this is a first attempt. And this is the fluorescence. Just to impress upon you that electron microscopy gives you information, this is a cancer cell called a HeLa cell, named after Henrietta Lacks. It's a very robust cancer cell, and we put little nanoparticles into this cancer cell. And so I'm going to show you a blow-up of that little square. And this is the electron microscope image, and these are our little nanoparticles, and that's the luminescence. We think we can get probably 5 or 10 nanometer resolution, 5 or 10 nanometer particles of different colors. That will be so cool, because now you can have a half a dozen proteins, but you have an electron microscope picture of what's going on. So that's another, and this was taken in very bad conditions where we weren't even using spectral filters or anything, or timing or anything. So it looks promising. I'm going to end here to pull way back from science and technology to remind you how important light is. It's synonymous with economic prosperity and civilization. If you have light, you have a lot of things. You have something to do at night, rather than the usual. Well, there's something amazing about sustainability. You can't have sustainability until the population stops growing. But we are finding out that wealthy people, no matter what culture, what religion, or everything, have fewer kids. It's due to many things. It's due to higher education of women. It's due to the fact that you're no longer worried about infant mortality. When you, as middle-class Americans, have a kid, you expect the kid to grow up and live to old age. You don't expect half of them to die. And you're afraid that you might have to pay for their college education. And you have late-night TV. So there's a very complex set of reasons why you have fewer kids. But being able to read at night is huge. This is a dark continent. So it graphically tells you where poverty is and where it's not. There are no people here because they're cowboys and they like Wyoming, but never mind that. And so this is to remind you, first, our lighting isn't very efficient. It's scattering too much back into space. But mostly it's to remind you that light at its fundamental level not only gave us photosynthesis, it gave us an entirely different, it liberated us from summer, winter, night and day. And that was a huge, huge thing that I had to end on. So thank you.